Hi, welcome to my channel with technology space with machine learning and artificial intelligence. So the today's topic is perfect models in digital twin. And this presentation I'm trying to investigate the relationship between the models coming from classical mechanics towards the machine learning models. Generally, we can categorize these machine learning models as digital twin in this discussion. So let's move on to the main topics in this presentation. So let's try to answer this first question about can we build perfect models. So before that, we may have to define what is the model. You probably know a model is some sort of a conceptual representation of a system. Let's elaborate that concept further. We can go further and say that a model is a description of a system supported by various mathematical concepts. You know, mathematics used as a language to describe various types of systems. In this type of mathematical models, also call these first principles model, because these are based on the theories of classical mechanics. The classical mechanics based on the physical laws such as mass balance, energy balance, heat transfer, and so on. So here I'm trying to represent how a system model and environments are related to each other. As you can see, the system is represented by a white box with a continuous line. So that means system is somewhat, let's say, well defined as an engineering application or engineering system. And then system is surrounded by the environment. So the interface between the environment and the system can be classified as a boundary of the system. And you can see the system boundaries are somewhat fixed, but the boundaries of an environment can be infinite. For example, if your system is a ship, then ship is navigating in ocean, so the ocean environment is somewhat infinite. Then the next step would be to develop a model using the physical laws. And then a model is represented by a white box with the dotted line. So that means it shows that model is some sort of conceptual representation of the system. And then often we want to simulate these models in a mathematical environment. So to do that, we need a simulated environment. So as you can see, the simulated environment, the boundaries are somewhat fixed because we may not be able to develop infinite environment for these models to simulate. Rather, we develop some sort of limited environment, which can be a representation of the actual environment itself. So I think in that slide we defined what is a model. So let's try to answer the question of can we create a perfect model. So if you are looking into various engineering applications, you can see these models being developed under classical mechanics under two levels. The first one is a top-down approach where you start with the whole initial system and then you kind of dismantle your system towards the materials. So that means you divide system into subsystem, subsystem into component and subcomponent and so on. And the second approach, which is I think the most popular one, is the bottom-up approach. Either it can start from materials to build up to the system, or it can start from some sort of a subcomponent layer and then go towards the systems. So that is the most common approach when you're developing mathematical models into these engineering applications. So that way you can create a series and parallel model structure for your system. So in that approach, what you generally do, you develop smaller mathematical models for various subcomponents, and then you combine or integrate these subcomponents into components and into subsystems and so on to develop this complex system model. So the answer to this question, can we create a perfect model under this type of approach? My answer would be probably not, because these are somewhat complex systems. So let's move on to the next slides to give some reasoning why this may not be a successful approach. Before that, I would say, like, is there a concept of a perfect model exist? You probably heard about this idea about this concept. All models are wrong, but some models are useful. Because when you are developing such type of a complex models, what happens eventually, you end up with a complex empirical model. The concept of empirical models are related to the observations, because instead of developing models based on physical laws, if you are deviating towards observations, just observations, then it become a more empirical model. So often when you're developing these empirical models, you might combine physical laws as well as the observations. And then when you develop these complex empirical models, often these models become somewhat fuzzy. I wouldn't say it, I mean, it may improve the performance of these models up to a certain level. After that, it its performance can degrade. So because of that reason, I am representing these empirical models in a somewhat with a fuzzy boundary conditions when you are developing such type of models. So let's try to define what is a useful model. Every model you develop, it should have a model or design objective or objectives. So that way, this model, a useful model, should satisfy its design objective. On the other hand, when you utilize the physical laws to develop these models, you may have additional assumptions, because this is where you kind of classify, this is where these physical laws will be limit the performance of these models. So that way, model should only satisfy its objective, but not every application these models going to be implemented. So then let's come back to that previous discussion on why not a perfect model. There are several reasons for that. And here I am identified 4 of those main reasons why we would not be able to develop a perfect model. So the first reason is system model uncertainties. And the second reason is model complexity versus development and maintenance cost issues. The third reason is error propagation. And the fourth reason is time variant features. So let's go through each one of these topics and elaborate a little bit further. So the system model uncertainties as the first reason. When you develop a model from a specific system, there's a higher possibility you might have a structural and parameter uncertainties. Structural uncertainty is often related to the structural differences between the system and the model. Parameter uncertainty is related to the differences between the system parameters and the model parameters. In general, when we develop a model, we want to know how accurate this model with respect to the its own system. So in that process, what we do generally, we observe the system performance in its own environment, and then we also observe the model performance in the simulated environment. And then we compare these performances. So if you see any differences between the system and model performances, what we do, we go back and update the model. So that way we would expect to adjust the structural as well as the parameter uncertainties in between the system and model. And some situations we might succeed, but often it may not be the case, because we may not have enough resources to develop these massively complex system models. So let's discuss the second reason. It's the model complexity versus development and maintenance cost. When you develop a more complex model with some empirical component, obviously your model complexity will increase. Then along with that complexity, the model development and maintenance cost also will increase exponentially. So at some point, it would not be practical for you to develop and maintain such type of a complex systems due to the cost factor that will influence your model development process. And this cost can also be the computational resources you may need to run and execute such type of complex models. So the third reason is the error propagation. When you build these complex models, which various smaller models to develop, let's say, the smallest building block in your model, and when you combine these building blocks, you might end up with subcomponents, components, subsystems, and systems. So there are different model layers in this type of complex systems. So when you're combining different types of models, we would expect the model performances will propagate throughout this type of a complex series and parallel network. But eventually what happens, the system and model uncertainties or the errors associated with these models will propagate through these complex networks. So eventually the system model performance will degrade because of this massive error propagation throughout these complex networks when utilizing these classical mechanics. So the next or the last reason is time variant feature. Here when you develop a specific model for a specific systems which is in a specific time instant, let's say in time t1, and when the system operate throughout some sort of a time interval, it might shift it towards a time t2. And such situation, the structure or the parameters in the system can vary. I mean, this may be due to some environmental effect. So the model you developed in the time instant, a previous time instant may not be applicable for this new time instant. So here we are assuming that there's no model update with respect to the system structural and parameter variations. So these model structural and parameter variations along the timeline can create another challenge in developing these perfect models. So let's try to relate a digital twin into the models that we have discussed under that classical mechanics. So the digital twin can be classified as a developing a system behavior from data sets. Since this is a pretty much data-driven approach, you may have to utilize extreme data or information from the systems that you have collected in this process. So if you ask the question, can we provide the solutions to the challenges that we have discussed previously under the digital twin? The answer would be yes, if the system behavior can be adequately represented by the data space that we are working with. So here the data space is represented by the extreme data and the information. We will have a separate discussion on what is extreme data and the information, but so for this stage, please stay with these notations. And then when you have extreme data sets, the next step would be to utilize this data. This is where the machine learning type of algorithms will come handy. And then it can provide a better approach to develop possible mathematical models into these type of systems. And then machine learning doesn't mean we are deviating from the physical laws. Actually, while we implementing the machine learning algorithms, we may need physical laws or the domain knowledge to utilize those algorithms in a better way, which will fit into the system structural and parameter conditions. In the same time, when you're developing these models, these models will have a specific model objective. So therefore, these models will not satisfy every applications that it would be used for. So there are specific model objectives, and these models will satisfy those model objectives. In the other hand, the various model assumptions will also be utilized, like in this previous step. Since this model development for the digital twin is pretty much a data-driven approach, in the initial stage we use this extreme data and the information, but then in a current state we might update the model based on the data and the information collected by the system. So this data is come as online data or the information, and then this information will feed back into the models to do the model update process. So that way I think we can develop almost near perfect models from this digital twin, which should be utilized towards various applications, still satisfying its own model or the design objectives. So let me go a little bit further and describing some features of the digital twin, what we would expect in the future. But and these features I will discuss separately in a future videos. So these features can be classified as a self-learning, self-cleaning, self-reduction, and self-visualization. Since these digital twins models are transforming data into a model itself, this model development process can be self-learning. That means we can develop machine learning algorithms and deploy into these data sets, and then these algorithms can identify these data sets and its own structure itself. So that way we can transform the data sets into a model itself. And then the second feature is the self-cleaning. Self-cleaning means when you deal with extreme data sets, the biggest problem you're going to face in these data sets is this quality of the data. Here I'm referring to various data anomalies. So the self-cleaning process should involve identifying such data anomalies as well as recovering these data anomalies, because a larger part of these extreme data sets could consist of various data anomalies. And then the third feature is the self-reduction. When you have these massive data-driven models, the sensor noise can be one of the challenges you might face. So reducing the dimensionalities of these data sets will eventually reduce the noise levels of the data. That would eventually end up in a better performing mathematical models for the respective systems. So the fourth feature would be self-visualizations. These extreme data sets existing in high dimensional space, so for humans it would be extremely difficult to imagine or visualize the information. So to make a proper approach to visualize these type of high dimensional data sets, this data may have to be projected into different visualization spaces. So that type of approach can be categorized as this self-visualization. So I think these are kind of 4 important features that might be utilized in the future to develop these digital twin models. So that's the end of my presentation. Hopefully you have enjoyed that. So if you are still interested, please stick around with this channel. Thank you.